Welcome back. We'll be looking at a few examples now covering definite integrals using integration by parts. And the first example that we'll be looking at today is the integral from 0 to 1 of tan inverse of x dx. Right. So using the same logic that we established previously for integration by parts, we'll have to find which function will let u be equal to and which one will be v. Using that logic, let's, for example, say that we let our u be equal to tan inverse of x. That would mean that our dv will just be dx, meaning that v will be x, right? And that means that our du will be 1 over 1 plus x squared dx, right? So going back to the original integral, we have the integral from 0 to 1 of tan inverse of x dx is therefore equal to u times v, which is x times tan inverse of x minus the integral from 0 to 1. Obviously, this is estimated between 0 and 1, minus the integral of 0 to 1 of v du, which is x over 1 plus x squared dx. And if we evaluate the second integral here, we can clearly see that this will be equal to x times tan inverse of x from 0 to 1 minus the integral of x over, the integral of x over, the integral of x over 1 plus x squared is, as you can see, the numerator is 1 degree lower than the denominator. So there's a way in which the numerator is the derivative of, is a form of the derivative of the denominator. And in that case, this integral should be equal to ln, right, of the denominator, right, but now divided by the 2 because we have an x squared there, right? So you have to go back to our to how we previously solved in these types of integrals to understand the thinking behind this. Right, so that is what that integral is equal to, and this is evaluated between 0 and 1. So that is therefore equal to if we take the higher limit of our first bracket here, we have 1 times tan inverse of 1, right, which we can just write as tan inverse of 1 minus 0 times tan inverse of 0, which will just be 0 there, minus ln, if we plug in the higher limit 1, we'll have ln of 2 over 2 minus ln of 1 over 2, which is 0. So that's what we're left with. And this is equal to tan inverse of 1 is pi over 4 minus ln of 2 over 2. So this is our final answer for this question. Now, looking at the second example, we have to find the integral from 1 to e of sine of ln of x. And we'll first start by letting this original integral be, let's call that I1. And let's use the substitution such that u is equal to sine of ln of x, in which case du is equal to 1 over x times cos of ln of x, right? Here we used the chain rule, which you can revisit, and dv will therefore be equal to just dx, meaning that v is equal to x. And the integral will therefore be equal to, if we rewrite this, u times v, which is x times sine of ln of x, minus the integral of v du, which is x multiplied by 1 over x cos ln of x dx. This is equal to x times sine of ln of x minus the integral of, obviously we can see that the x can cancel here, so we have the integral of cos of ln of x dx. And this is as far as we can take that for now. So we'll have to evaluate this second integral separately and then just bring back the solution into this expression. So let's evaluate the integral. Obviously, this is all evaluated between 1 and e, 1 and e, 1 and e, 1 and e. The integral from 1 to e of cos of ln of x dx. Using the same logic for our substitution, we let u be equal to cos of ln of x, meaning that du is equal to 1 negative 1 over x sine of ln of x, and dv is equal to dx, which means that v is equal to x once again. And that would mean that this integral from 1 to e cos of ln of x dx is equal to u times v, which means x times cos of ln of x minus v du, which is x multiplied by negative 1 over x times sine of ln of x dx, which is equal to x times cos of ln of x minus, so that's plus, the integral of, the x can cancel as well, so the integral of sine of ln of x dx, which is from evaluated from 1 to e, sorry. I keep forgetting it, but please remember it when you're solving it. From 1 to e, right? Now, we note that this is the original I integral that we had. So knowing that, we have originally that I therefore is equal to, let's go back to the original integral, I is equal to, right, x times sine of ln of x evaluated from 1 to e minus this entire integral, which we found to be x cos of ln of x evaluated between 1 and e minus the integral, this integral which we called, we denoted as I, so minus I, right? So that's what we have. Now taking the I to the right hand side, we have 2I is equal to x, and putting all of this under the same brackets, we have x sine of ln of x minus x cos of ln of x, all evaluated between 1 and e, and this just means that I is equal to 1 over 2 x sine of ln of x minus x cos of ln of x evaluated between 1 and e. And once you do the substitution, you should be able to get that I, which is our original integral, which was the integral from 1 to e of x, of sine of ln of x dx is just equal to 1 over 2 multiplied into e of sine of 1 minus e of cos of 1 plus 1. Right, so please double check this result. And yeah, let's move on to the next example, which is asking us to find the integral from 0 to 1 of the square root of x multiplied by sine of pi times square root of x. So how do we go about this? Well, we use the same logic. Once again, integration by substitution is what we'll be using here, and we'll be saying that let's let u in our case be equal to let u be equal to the square root of x, right? So first, I think the first step in this case will be first to try to simplify our expression in such a way that we get rid of the square root here, because this square root might make our solution difficult. So we'll try using what we call the u substitution, but we'll just call it w, just so we don't confuse it with the u of the integration by parts. So let's call it the w substitution, and we let w be equal to the square root of x, which means that dw will be equal to 1 over 2 root x dx, right? Meaning that dx will just be equal to 2 root x dw. Okay. Right, so taking it to the original integral, we have the integral from 0 to 1 of w times sine of pi w multiplied by dx, which is 2 times root x, which is w, so 2 times w dw, and this is therefore equal to the integral from 0 to 1 of 2 w, sorry, not, I keep, this is a w, not omega, w. So the 2w squared multiplied by sine of pi w dw, right? And now we can use our integration by parts by letting our u be equal to w squared, and which means that our du will be 2w dw, and we let our dv be equal to sine of pi w dw, meaning that our v will be equal to negative 1 over pi cos of pi w. And knowing all of this, our integral would therefore be equal, right? So the integral from 0 to 1 of 2w squared sine pi w dw will be equal to u times v, which is w squared, negative w squared over pi multiplied by cos of pi w, right, minus v du, which is 2w times negative 1 over pi times cos of pi w dw, and this will just be equal. Again, this is all evaluated between 0 and 1. I just keep forgetting to include it. So the integral becomes negative w squared over pi, over pi cos multiplied by cos pi w, evaluated between 0 and 1, minus, we can take out the, it's going to be the minus there, so it's going to be minus minus, so plus, multiplied by the 2, so that's 2, multiplied by the integral from 0 to 1 of w. You can take out the pi as well because it's a constant, so 2 over pi here, w multiplied by cos pi w dw. Right. Let me just double check this. And there's a two that I forgot to include here. So you have to pay attention to this. So there's a 2 there, a 2 there. This is this 2 that has to appear there as well. It's already showing there, so it should be there as well. So pay attention to that. Right. Okay, so now we'll have to evaluate this separately. So when we evaluate the integral from 0 to 1 of w times cos of pi w dw, using the same substitution, we let our w be equal to u, meaning that dw is equal to du, and we let our dv be equal to cos of pi w dw, which means that our v will just be sine of pi w divided by pi. And now that we have that, this means that the integral from 0 to 1 of w times cos pi w dw will be u times v, which means w times sine of pi w divided by pi minus the integral of v du, which is sine of pi w divided by pi times dw. Right. And of course, this is all evaluated, excuse me, this is all evaluated between 0 and 1, 0 and 1. This is equal to w sine of pi w divided by pi, evaluated between 0 and 1, minus, I can take out the 1 over pi, which is a constant, so minus 1 over pi, multiplied by the integral of sine pi w, which will just be negative cos pi w divided by pi, evaluated between 0 and 1. Right. So let's make some more room here. Right. Okay. So now that we have that, we have to go back to the original question, which was this integral here. So let's copy that. So the integral from 0 to 1 of 2w sine of pi w dw 2w squared, yes. And we found that the first section was equal to 2 multiplied by negative w squared over pi times cos of pi w evaluated between 0 and 1, right? Plus 2 over pi multiplied by that integral, which we found to be w sine of pi w divided by pi evaluated between 0 and 1 minus 2 over pi multiplied by that. So we have minus minus, so that's a positive 2 over pi cubed, right? We have 3 pi's now. Multiplied by cos of pi, so multiplied by cos of pi w evaluated between 0 and 1. Let me just double check that the work is all correct. Yeah, looks good. So now if you evaluate this with the boundaries, you should be able to find 2 over pi minus 4 over pi cubed minus 4 over pi cubed. Just give me a minute. Right, which will be equal to pi cubed all to the pi cubed, 2 pi squared minus 8, which should be the answer there. Yeah, and that should be the final answer. So once again, you can double check the calculations. It's possible that there might be mistakes, but the overall method and the procedure should be correct, right? So you can just go through the solution again and try to see if we made any mistakes anywhere, right? Yes, so please double check this result and yeah, figure out if there were any mistakes we made along the way. Right, thank you for watching. I'll see you in the next video. Thank you. Bye.